momentum and impulse. Okay, so curriculum. Define momentum as a vector quantity equal to the mass and the velocity of the object. Analyze graphs that illustrate a relationship between force and time in collision. So this is important. You need to know force-time graphs. Okay, so I got some questions for you. So what does momentum mean to you in your own words, right? So obviously you're watching a video and I can't ask you this question, but think of like sports momentum, right? When a team really gets going, right? So they're going fast, they seem really big. That's what momentum sort of means to me, right? How do you increase the momentum of something? Well, you need to make it bigger or go faster, right? So what is more momentum, a cruise ship or a car? Well, the cruise ship seems bigger, so that's going to have way more momentum. Even though the car is going fast, the cruise ship is just so big, that seems like it's going to have a big impact on momentum. And that's exactly what momentum is. So momentum is simply the mass of an object multiplied by its velocity. It's sort of a made-up physics thing that it's like energy. When I talk about energy in Physics 20, I say that it's kind of just like a bookkeeping method. It's a way to analyze how things are transferred. Well, momentum's kind of like energy. It's just this like made-up thing that physicists use that work, that we can sort of analyze things and analyze conservation of momentum and how it moves, how it's transferred, things like that. So you'll notice that M is already used up, so this is mass, right? So we can't use M again for momentum, so momentum uses P as its symbol. So momentum is a vector quantity, which means direction matters. So in stating an object's momentum, you have to include a direction. And there's going to be questions on your test where I ask for the momentum, and you just give me a magnitude, and you don't give me a direction, and you get marks taken off because you don't do that, right? So the direction is really easy to figure out, right? So if there's an object that's flying like this, so sort of like a projectile motion, well, initially it's going up, so it's got its velocity up, and then it's slowing down, and then it stops, and then it starts moving downwards like that, and it's also got a momentum, a velocity in the x, so this is our vx, this is our vy, and no forces act on it in the x, so our vx just stays the same the entire time, right? That's how we practice drawing that in Physics 20. Well, momentum is just momentum equals mass times velocity. So mass is a scalar quantity that doesn't have direction. So whatever direction the velocity has is the direction the momentum's going to have, right? So we're going to have this momentum in our x that's not changing, right? Our momentum's just staying the same. And then in the y, we have a momentum up, less momentum up, no momentum up, and then we have momentum down, right? It's the same thing as the velocity vector arrows. The direction of the velocity is going to be the direction of your momentum. So we'll start off with some easy questions. So a 50-kilogram boy is running 11 meters per second north. What is his momentum? Well, this is nice and easy. P equals mv, right? The mass of the boy is 50 kilograms. The speed is 11 meters per second. Right? So 50 times 11 is going to give us 550. We don't have any special units for momentum. It's just kilograms, meters per second. Right? And lots of people do this, and then they get the wrong answer. What am I missing? Direction, right? If my velocity is north, then my momentum is also north as well. A 200-kilogram man is running and has a kinetic energy of 12 joules. What is the momentum of the man? Well, now we can use our kinetic energy formula, right? We know that EK is equal to 1/2 mv squared. So we know the kinetic energy, we know the mass, so we can figure out the speed. So we move our 2 up top, we move our mass down below, and we square root it, and we get that. So 2 times 12 joules divided by our mass of 200 kilograms, and we square root it, and we can find our v. So I'm just going to open our calculator so we can find out the speed. Right, and once we find the speed, well, we wait for that to open up. P equals mv. Right, so once we find the speed, we just have to multiply it by the mass, which is 200 kilograms. Oops. So there it is. So 2 times 125, or 12, can't read my own writing, this 12 joules, 2 times 12 joules, divided by 200, and square root that answer. So that's our speed, and the person is 200 kilograms. So our answer is, we have 2 sig digs, is 69 momentum kilograms meters per second. So here's a board question. Give it a go, see if you can do it, and answer the question. So determine the ball's momentum before it hits the ground. So we need P equals mv. We have the mass of the ball, but we just don't have the speed. Right? So there's a couple ways you can do this. The ball is dropped from a height of 10 meters. So you could do VI, VF, DAT if you wanted to. Right? The initial velocity is 0. The height is 10 meters. The acceleration is 9.81 meters per second squared. We'd want to find what's the final velocity, so we'd use VF squared equals VI squared plus 2AD. Our initial is 0, so we can get rid of it. And to get rid of the square root, or squared, we'd square root it, so we get VF equals square root 2AD. Or you can see this is a conservation of energy question. Well, at the top, it's got potential energy. At the bottom, it's got kinetic energy. mgh equals 1/2 mv squared. Our mass cancels out. Right? To find our speed, I'll move 2 up there, and then square root it. So we get square root 2gh equals v. Well, 2, g, a, same thing. Height, distance, same thing. Square root. No matter how you do it, you get the same thing. So if we plug that all in, so 2 times 9.81 times our height of 10 meters, and we square root it. We find our speed is 14. We multiply that by our mass, which is 10. We have 3 sig digs. We want to find our momentum, and it's going to be 140 kilograms meters per second, and it's obviously moving down in this situation, so we'd want to add that. Okay. Oh, I forgot to mention. I forgot to talk about direction, right? So it's asking for the momentum, but it needs direction. But there's a flaw to this question, right? When we talk about energy, energy is a scalar quantity, right? So the man is running, but the direction doesn't matter with energy. So this is flawed because we don't know the direction. So how do we answer with the direction? So this can be solved with the magnitude of momentum of the man. That would be a better question in this situation because energy is scalar. You can't get a direction from that. So yeah, that's why I left that out. Okay, this one, we do know that it's moving down. Even though it's an energy question, it's going to be moving down, so we can get that from this question. Okay, the distance a 2,000 kilogram car travels over a period of time is given by the following distance versus time graph. What is the momentum at 5 seconds? So here is 5 seconds. So we need to know, okay, they give us a distance time graph. There's 3 things we can find from this distance time graph. We can find slope, we can find area, and we can find our y value. So our y value just tells us at 5 seconds, it looks like it's like 45 meters, so that looks like distance. Slope is change in y over change in x. So if we look at the units, y is in meters, x is in seconds. Oh, looks like our slope is going to give us our speed, and we actually need that. Okay, so what is momentum at 5 seconds? Well, I can just use p equals mv. If my slope gives me my speed, so let's find slope, y2 minus y1 over x2 minus x1. So I will use, the speed doesn't change, the slope doesn't change this entire time. So I'm going to use 60 meters minus 30 meters over 7 seconds minus 3 seconds. And I'll plug that into our calculator. 60 minus 30 divided by 4. 7 minus 3 is 4. So we end up getting that as moving 7.5 meters per second during this time. So then I can just go 2,000 kilograms times 7.5 meters per second. And I would get 1.5 times 10 to the 4 kilograms meters per second. Right? And because I have a positive slope, we can say that it's moving forwards. Okay? It's a positive velocity, positive slope, moving forwards. So I can throw another random graph at you. So we have momentum versus speed, which we're not really familiar with. So another way that we can do this question is we can analyze it using y equals mx, right? So to use y equals mx, we need a formula with momentum and speed in it. So we can use p equals mv. To make sure this is in y equals mx form, we need to make sure that our y value is isolated, which it is. Our y value is momentum. So this is our y value. And then our x value is speed. So m is m. So it looks like slope is equal to mass. Right? So all that we would have to do is we would have to find the slope of this line. So I'll use this as 0.2. This is a terrible graph. We'll say that this is basically 0, 0. So again, y2 minus y1 over x2 minus x1. y2 looks to be about, I don't know if my line's crooked, about 0.40 minus 0. And 0.40 is in kilograms meters per second. And then 1 meters per second minus 0. So it's just 0.4 divided by 1. Right? We can only be as accurate as our graph is. Obviously, there's no like cross sections in this graph, so it's not going to be very accurate. Why am I typing this into my calculator? So our answer is 0.4 kilograms. Right? We know it's kilograms because we want to find our mass, but if we want to take a look, right? So on top, we had kilograms, meters per second, and then on the bottom, we had meters per second. If we have 1 over seconds, we can move that seconds to the top. Same thing. Seconds cancels out, meters cancels out, and we end up with kilograms. Okay, so I got a couple more questions for you. Would you rather fall on concrete or grass? Hopefully it's grass. Why? Grass is squishier, right? Concrete's harder. It's going to hurt more to fall on something that's harder. You're holding a teacup and suddenly drop it. What would be your last resort to stop it from breaking? So most people, when doing this, they would kick out their foot, right, to try to slow it down slower, right? If it just hits the ground, it's going to smash instantly. But if you can use your foot and sort of brace it a little bit, you can slow it down over a longer amount of time. So by doing this, what you're thinking about is you're thinking of a physics concept called impulse, even though you don't know what impulse is. So what impulse is, sometimes we are more concerned with the change in an object's momentum rather than the actual momentum itself. That change is very important. So since an object's mass is usually constant, changes in momentum usually arise from changes in velocity or accelerating objects. So the change in momentum is given a special name, which is impulse, right? So impulse has a symbol delta P. So this is a symbol for impulse. And impulse is just change in momentum, right? So I can switch my P equals mv formula into an impulse formula. My change in momentum is going to have to do with my change in velocity. And remember, change is equal to final minus initial. That's important, right? So my change in velocity would be velocity final minus velocity initial. So this is our formula. It's still P equals mv, only we throw those deltas on there, those changes. So we have final minus initial. So we can derive another formula for impulse using Newton's second law. So Newton's second law is force equals mass times acceleration. And one of the most simplest formulas for acceleration is change in velocity, right? So change in velocity over time. So if I move my time up here, well, look at that. Mass times change in velocity, that's impulse. So if this equals impulse, then this also equals impulse. So we end up getting this new formula for impulse, and this was the one we already had. Right? So we have impulse equals mass times change in velocity. We have impulse equals force times change in time. Right? And what we can do is we can also sandwich them together, and we can say that these equal this. And what you need is you need all three of these. Sometimes you need to use it like this. Sometimes you need to use it like this. Sometimes you need to use it like this. But this is the only one that's in your data book. Okay? These aren't given in your data book, but you still need to know that this is impulse, and you'd still have to figure it out that way. Okay? So delta P is impulse. M is mass, delta V is change in velocity, F is our net force, and delta T is our change in time. The reason I don't put this delta here for time very often because it's time final minus time initial, but I've never actually seen a question where my time initial isn't 0. So if it's 0, our time final is our change in time, so I just leave it out, right? It's a waste of time. Why would you not start at 0? Okay, so we're going to look at a Spider-Man comic that it's Green Goblin versus Spider-Man, but what it actually is it's Impulse versus Spider-Man. So here's Gwen Stacy, Spider-Man's girlfriend, being thrown off a bridge by the Green Goblin. And Spider-Man says, "Gwen, no, I've got to catch her." That's his webbing. "Stop her before she hits the water. I've got to. I did it." Swick, right? Caught her around the legs. "Spider powers, I love you. Not only am I the most dashing hero on 2 legs." Oh, what's this? Right by her neck, there's a snap. Oh, she looks kind of limp right there. This is very dark, by the way. "I'm easily the most versatile. Who else could have saved a fallen girl from certain death? Gwen? Hey, kid. What's wrong? Don't you understand? I saved you. You can't be. No. Oh, no. Don't be dead. Gwen, I don't want you to be dead. I saved you, honey. Don't you see?" And then in flies Green Goblin. "Romantic idiot. She was dead before her webbing reached her." Yeah, well, I guess, sort of. Not really. "A fall from that height would kill anyone before they struck the ground. But for you, my friend, death will come more quickly and more surely than the shock of a sudden fall." Wrong, Goblin. So what the heck happened to Gwen Stacy, right? So let's do some physics to find out why her neck snapped here. Okay, so we need to figure out Gwen's final speed. So if we take a look at the bridge here, so this looks like a pretty big bridge. I would say that this probably has a distance of, I don't know, about 100 meters. Right, so just like that board question that we did, we can do it using VI, VF, DAT. We can use our energy before equals our energy after. Right, before she has potential energy, after she has kinetic, mgh equals 1/2 mv squared. If we want to find our final speed, our mass cancels out. We move our 2 up there, and we square root it, so we get square root 2gh is equal to v. So 2 times 9.81, because Spider-Man lives in New York, so that would definitely, it's not like Marvel Cinematic Universe where it might have a different g. And then our height, I said the bridge was about 100 meters. We square root it, and we can find our speed. So how fast would Gwen be moving if she fell from a 100-meter bridge? So 2 times 9.81 times 100 square root. So Gwen Stacy would be going about 44 meters per second. Okay, that's how fast she would be going, around 44 meters per second. So we can assume that Gwen has a mass of about 50 kilograms, and Spider-Man's webbing took about 0.5 seconds to stop her. So what we're going to find is we're going to find the force exerted on Gwen. So we can use our new impulse formula, where force times time is equal to mass times change in velocity. So if we're solving for force, we want to move our time down below. So what we're talking about here, the 0.5 seconds is the time it took. Here we go. So the webbing, here's the webbing. It contacted her, right? There she's moving super fast. And then, so this is our initial speed, right, when the webbing contacts at her. And then our final speed is when she stopped at the end there. Okay, that's important. It's not as she's falling, right? Because this is 44 meters per second, and our final speed is 0 meters per second, right? Which is a little bit different if we were trying to calculate how fast we were going. Here she starts at 0, and then her final speed would be the 44 meters per second. We're talking about when the web is in contact with her, okay? So her mass is 50 kilograms. We can break this into final minus initial. Sorry, that's messy. Final minus initial. So my final speed is 0. My initial speed is at 44 meters per second. Right? And then the time is 0.5 seconds. So if we calculate that, and we don't need our full answer because we're not accurate. We said it was like roughly 100 meters. 44 is good enough, right? So it's going to be 50, and 0 minus 44 is going to give us negative 44, divided by 0.5. So the force exerted on Gwen, well, why is it negative? Well, we'll talk about that. So it's 4400, right? Or 4.4 kilonewtons, and it's negative. Well, what does that mean? Well, we're saying that this is positive, right? So this is positive. She's moving downwards, so we're saying downward is positive. And also calculating this, we said this is positive, it's downwards. So downwards is positive, so the negative must mean that the force is up, which makes sense because that force is stopping. It's bringing her back up again. So 44 kilonewtons. We don't use newtons a lot in everyday life, but what we do know about is we know about her normal weight. So Gwen Stacy's normal weight is just 50 times 9.81. So this is a force that she feels every day, right? This is a force that she experiences when Spider-Man is stopping her. So if we just take our 440 and divide it by our smaller one, right? Our bigger one divided by the smaller one, the negative doesn't matter. So what she's experiencing is a force about 9 Gs, 9 times regular gravity, right? That's a pretty big force. If this was a roller coaster, you'd be blacking out for sure. So most of this force goes to the weakest part in her body, and the weakest part in her body is her neck here. So she's experiencing 9 Gs. Her neck snaps. It makes sense that she would have died, right? So what can we do in order to stop Gwen Stacy from dying? How can we decrease this force, right? Well, we can't do anything about her mass, right? She's 50 kilograms, and we can't do anything about her change in speed, right? If she falls from there, she's going to be going 44 meters per second, and we're going to stop her. So we can't do anything about that, but what we can do is something about time. So if I want to decrease my force because they have an inverse relationship, I need to increase my time, right? And if I go 50 kilograms times 0 minus 44 meters per second, and let's say I go make her stop in 2 seconds. Sorry, that's an S. That's a terrible S. It looks like 25. Let me try again. Yeah, it's still pretty bad. So let's 4 times the time. If we 4 times the time, we're going to 1/4 the force. but we'll just type it in anyway. So 55, or 50 times negative 44. And then we divide it by 2 seconds, right? We get that 50 times 9.81, so her normal weight that she feels every day. 50 times 9.81. So if we do this divided by this, right? She's feeling about 2.2 Gs. So 2.2 Gs is kind of what you'd feel in a roller coaster. She'd feel like her neck snap a little bit, but nothing too crazy. So 2.2 Gs is definitely doable. So that would help her, right? So that's what we need to do to decrease our forces. We need to increase our time. And that's why when you go bungee jumping, you don't use a rope tied to your legs, right? That would just pop your legs right out of their socket. You use a stretchy cable that slows things down, right? It takes longer to stop, and that's going to decrease the force on your body. So that's what we do. So this is a later Spider-Man comic. He kind of learns from his mistakes. So if I swing in to grab him, the difference in our momentums will take whatever part I grab with me, but leave the rest behind. Not really sure what he means there. First, I have to slow down to his speed, then grab him and swing away. Now the line. So what he's doing differently here is Spider-Man has super strength. So Spider-Man might be able to handle 9 Gs. I'd like to see this hand a little bit higher around his neck, kind of like he's cushioning a baby so the neck doesn't snap again. But because he's extra strong, he would be able to handle that extra speed even if he couldn't make his webbing stretchier like that. So yeah, he did learn from his mistakes. So what if Spider-Man had made the cord more like a bungee cable? How would that make a difference? Well, we already talked about that. So we need to increase our time, which decreases our force. That's what we need to do. Okay, and let's do a couple other questions, just some impulse questions. So a 150 kilogram baseball is pitched horizontally at 40 meters per second to the batter, who hits it back at the pitcher at 80 meters per second. If the bat and the ball were in contact for 0.8 milliseconds, so this is millis times 10 to the negative 3 seconds, what was the impulse delivered to the ball by the bat, the average force delivered by the bat to the ball, and the average acceleration of the ball during its contact with the bat? Okay. So for this one, I'm going to switch to my whiteboard, because there's a few more calculations and I don't have a lot of space here. So first thing I'm going to do is I'm going to draw a picture. So we have 150 kilogram baseballs pitched horizontally at the batter. So we have our pitcher, right, who's throwing the ball, and initially the ball is going 40 meters per second. Okay. There's a batter who hits it back. So there's a bat, and then he hits it back at 80 meters per second. Cool. So very first thing I want to do with this question, and any question like this, is you need to make sure that you set a positive and a negative, right? It doesn't matter what you set, but because momentum and impulse are vectors, we want to say, okay, this is positive, this is negative. So the baseball is going this way, it's negative. The baseball is going that way, it's positive. That is a very, very important part of the question. So now, if we want to find our impulse, we have two formulas. Mass times change in velocity, and impulse is equal to force times time. Right? We don't have any forces. We do have a time, but we don't have forces. We do have a mass and a velocity, so this one is the one that we want to use first. So to do this one, I have my 0.150 kilogram baseball. And my change in velocity is going to be final minus initial, right? Remember that it's final minus initial. So my final speed is negative 80 meters per second, and my initial speed is positive 40. If I don't put those positives and negatives in there, I'm going to get the wrong answer. So if I type that in, 0.15 times throw these in brackets, negative 80 minus 40. And you end up getting negative 18. So my impulse is negative 18 kilograms meters per second. And what does that negative represent? Well, this is our pitcher, this is our batter. So the negative would be towards pitcher. And that's what they used in the question, so we should keep that the same. Okay, so the second part of the question is asking the average force delivered by the bat to the ball. Right? So if we want to find force, well, what we have to do is we're going to use this. Now that we know impulse and we know time, right, we can move that time underneath there. We can find the force because that impulse to change in momentum is going 40, going 40, going 40, going 40, going 40. He hits it, and then now it's going negative 80, negative 80. That impulse, that change in momentum happens as the ball is in contact with the bat. So our impulse is negative 18 kilograms meters per second. Our time in the question was 0.8 milliseconds, so times 10 to the negative 3 seconds. So all I have to do is take my negative 18 and divide it by our time, 0.8 milliseconds. Right, so it looks like our force is 22500. Right, so that's newtons, or we could say negative 22.5 kilonewtons. Right, that's a nice way of putting it in there. And the negative again represents towards pitcher. Okay, you need that direction in there. And the last part of the question, it says the average acceleration of the ball during its contact with the bat. So I'm just going to do that last part up here. Well, we know force equals mass times acceleration. So we have our net force, right? Our net force is just going to be by the bat. We divide it by the mass of the ball. So we take our 22500 newtons. We divide it by our mass, which is 0.150 kilograms. And we plug that into our calculator. So we take this, divide it by this, and we get our acceleration, which is 5, negative 1.5 times 10 to the 5 meters per second squared. You can't really go like kilometers per second squared or anything like that. It just doesn't work like with newtons. Acceleration is a vector. That negative still is important. So again, we would put towards pitcher. Anything that's a vector, I need a direction. Don't forget that on your test. Okay. So just a couple more questions. So here's a board question for you. So give this a go, pause the video, and see if you know how to do it. So a 12 kilogram tennis ball, that's really heavy, is traveling 12 meters per second east when it's hit back and given a velocity of west. So we have east and west here. So north, east, southwest. So I'll make the east positive and the west negative. So east is positive, so this is positive. This is negative. What is the impulse? Well, impulse is equal to mass times change in velocity. So 12 kilograms. It's probably supposed to be 0.12, but whatever. 12 kilograms. So change in velocity is velocity final minus velocity initial. So my final velocity is negative 22 meters per second. And my initial velocity is positive 12 meters per second. So I plug that into the calculator. Negative 22 minus 12 times by 12. And I get negative 408 kilograms meters per second. And that negative must mean that it's going to the west, because I said negatives are west. Okay, that's how you do that question. So a graph question here. What does the what impulse does a puck receive from the hockey stick? And assuming that it starts from rest, what is the final speed of the puck? Okay, so we have a force versus time graph, right? And again, we can look at slope, we can look at area, and we can look at y value. So y value just tells you at 2 seconds there's a force of 50. That one's out. Area is y times x, right? So my y is force, and then my x is time. What does force times time equal? Well, that equals impulse. So you need to know that. You need to memorize that. If you want to find impulse on a force versus time graph, you need to find the area under the graph. So there's a whole bunch of different areas here. So what we have to do is we have to break them into things that we can actually find. And then this little one up top would be 5 because we get a triangle rectangle combo. So I'm going to switch again to my whiteboard. And what we need to do is we need to find the areas of all of those. So to find the areas of all of those, we just need to know if they're a triangle or a rectangle. So the first one is a triangle. So to find one, that's going to be base times height divided by 2 because it's a triangle. And my base is 2 seconds. And my height goes up to 50 newtons divided by 2. So that's going to give me 50 kilograms meters per second. Oh, but I almost forgot one thing. I didn't look at my units on my x, and it's not 2. It's 2 times 10 to the negative 2 seconds. So you got to be careful with that because I've done this question a million times and I still make that mistake. So if I go 2 times 10 to the negative 2 times 50 divided by 2, that'll give us 0.50 kilograms meters per second. Okay, got to watch out for those units. 2 looks like a rectangle. So it's just going to be base times height. 2 times 10 to the negative 2 seconds is its base because it goes from 2 to 4. And its height is 50 newtons. So that's going to be double that. That's going to be 1. 3 is, oops, what did I label as 3? Yeah, 3 is that one. So 3 is also a rectangle. So 3 is going to be base times height. So its base is 1. And its height goes up to 50. So that's going to be 0.5 times 10, 0.5 kilograms meters per second. And then 4 was that last triangle, so that's going to be base times height divided by 2. Its base is 2. And its height is 60. And I divide it by 2, and that's going to be 0.60 kilograms meters per second. And then my last one is just that little triangle on top. So its base is 1. And its height, it goes from 50 to 60, so 10 newtons divided by 2. And then that is going to give me 0.05 kilograms meters per second. Okay, so then what I do is I add all those guys up. So this is 0.5, 1.5, 2, 2.6. Oops, that's a little bit off the screen. 2.65 kilograms meters per second. Okay, sorry, that's blocking a little bit. I'll just write it up here, 2.65 kilograms meters per second when I add those up. So that's how you find impulse using a force versus time graph. Okay, the second part of this question says, assuming the puck starts from rest, what is the final speed of the puck? So to do that, we can just use impulse equals our mass times change in velocity, so that's final minus initial, right? It starts from rest, so So this is 0. So really all you have to do is take that impulse divided by the mass when it starts at 0, and we get our final velocity. So if we take this and we divide it by 0.3, that would be the easiest way of doing this question. So 2.65 divided by 0.3, and you end up getting 8.8 meters per second. Sorry, so after I've done this question, I want to check, did I do everything that I should do? Well, this is my impulse, but impulse is a vector, and it has a positive force. Like if we take a look at the graph, right, all of this is a positive force. A positive force would mean that we're going forwards, right? If it was a backwards force, it would be under the x-axis. So I should also add forwards to this with my final answer. This was just speed, so I don't have to worry about vectors, but don't lose marks by forgetting to put in vectors. It's the worst way to lose marks. So I have one final board question for you. Find the impulse a 10 kilogram mass receives at 23 seconds. So again, it's a graph that we might not be familiar with. So pause the video, see if you can do it. Remember, the three things that we can find from a graph we might not be familiar with are slope, area, and y value. Impulse is equal to mass times change in velocity. So velocity would be important again, and velocity, well, at 5 seconds here, I'm going 3 meters per second. Yeah, velocity is just our y value. So we want to look at y value in this situation. So it's talking about 23 seconds. So 23 seconds, let me just switch my color. Oops. So 23 seconds is right here, right? And then what happens is here, it's going negative 11 meters per second. Here it's going 10 meters per second. So at 23, it changes speeds. So impulse equals mass times change in velocity. Well, my mass is 10 kilograms. And my final speed minus my initial speed is my change in velocity. Well, my final speed is 10 meters per second. And my initial speed is negative 11 meters per second. Right? Minus a negative is plus a positive. So this would be 21. So my impulse would be 210 kilograms meters per second. Okay, that's how you do that one. That is it. These are your questions. Here are your momentum ones. And then here are your impulse ones. That's your homework. Let me know if you have any troubles.